About 3 years ago, Wolfgang, Wolfi, Mittig and Yassid Ayyad went looking for the universe's missing mass, better known as dark matter, in the heart of an atom. Well, at least an explanation that everyone could agree on. "It's been something like a detective story," said Mittig, a Hanna Distinguished Professor in Michigan State University's Department of Physics and Astronomy and a faculty member at the Facility for Rare Isotope Beams, or FRIB. "We started out looking for dark matter and we didn't find it," he said. "Instead, we found other things that have been challenging for theory to explain. So the team got back to work, doing more experiments, gathering more evidence to make their discovery make sense." Working at NSCL, the team found a new path to their unexpected destination, which they detailed June 28 in the journal Physical Review Letters. In doing so, they also revealed interesting physics that's afoot in the ultra-small quantum realm of subatomic particles. "Shot in the dark matter is one of the most famous things in the universe that we know the least about. For decades, scientists have known that the cosmos contains more mass than we can see based on the trajectories of stars and galaxies. For gravity to keep the celestial objects tethered to their paths, there had to be unseen mass and a lot of it, 6 times the amount of regular matter that we can observe, measure and characterize. Although scientists are convinced dark matter is out there, they have yet to find where and devise how to detect it directly. Finding dark matter is one of the major goals of physics," said Ayyad, a nuclear physics researcher at the Galician Institute of High Energy Physics, or IGFAE, of the University of Santiago de Compostela in Spain. Speaking in round numbers, scientists have launched about 100 experiments to try to illuminate what exactly dark matter is, Mittig said. "None of them has succeeded after 20, 30, 40 years of research," he said. "But there was a theory, a very hypothetical idea, that you could observe dark matter with a very particular type of nucleus," said Ayyad, who was previously a detector systems physicist at NSCL. The researchers had a good chance of discovering something new. The question was what that would be. Help from a halo. When people imagine a nucleus, many may think of a lumpy ball made up of protons and neutrons, Ayyad said. It keeps 10 of those 11 nuclear particles in a tight central cluster. But one neutron floats far away from that core, loosely bound to the rest of the nucleus. Kind of like the moon ringing around the Earth, Ayyad said. And they did find a decay with unexpectedly high probability, but it wasn't a dark decay. It looked like the beryllium-11's loosely bound neutron was ejecting an electron like normal beta decay, yet the beryllium wasn't following the known decay path to boron. For anyone keeping score, that meant the nucleus had once again become beryllium. Only now it had 6 neutrons instead of 7. This happens just because of the halo nucleus, Ayyad said. It's a very exotic type of radioactivity. It was actually the first direct evidence of proton radioactivity from a neutron-rich nucleus. But science welcomes scrutiny and skepticism, and the team's 2019 report was met with a healthy dose of both. We had a lot of long discussions, Mittig said. It was a good thing. As beneficial as the discussions were, and continue to be, Mittig and Ayyad knew they'd have to generate more evidence to support their results and hypothesis. They'd have to design new experiments. The NSCL experiments in the team's 2019 experiment, TRIUMF, generated a beam of beryllium-11 nuclei that the team directed into a detection chamber where researchers observed different possible decay routes. That included the beta decay to proton emission process that created beryllium-10. For the new experiments, which took place in August 2021, The team's idea was to essentially run the time-reversed reaction. That is, the researchers would start with beryllium-10 nuclei and add a proton. Collaborators in Switzerland created a source of beryllium-10, which has a half-life of 1.4 million years, that NSCL could then use to produce radioactive beams with new reaccelerator technology. The technology evaporated and injected the beryllium into an accelerator and made it possible for researchers to make a highly sensitive measurement. It would even spit the proton back out, which can be detected as signature of the process. The results of the two experiments are very compatible, Ayyad said. Then we reached out to the Florida State team and worked out a way to support each other. The two teams were in touch as they developed their reports, and both scientific publications now appear in the same issue of Physical Review Letters. And the new results are already generating a buzz in the community. The work is getting a lot of attention. Wolfi will visit Spain in a few weeks to talk about this, Ayyad said. An open case on open quantum systems. Part of the excitement is because the team's work could provide a new case study for what are known as open quantum systems. It's an intimidating name, but the concept can be thought of like the old adage, nothing exists in a vacuum. Quantum physics has provided a framework to understand the incredibly tiny components of nature – atoms, molecules and much, much more. This understanding has advanced virtually every realm of physical science, including energy, chemistry and materials science. Much of that framework, however, was developed considering simplified scenarios. The super-small system of interest would be isolated in some way from the ocean of input provided by the world around it. In studying open quantum systems, physicists are venturing away from idealized scenarios and into the complexity of reality. To complete the case, researchers still need more data, more evidence to make full sense of what they're seeing. That means Ayyad and Mittig are still doing what they do best and investigating. "We're going ahead and making new experiments," said Mittig. The theme through all of this is that it's important to have good experiments with strong analysis. Y. Ayyad, W. Mittig, T. Tang, B. Olizola, G. Potel, N. Rijal, N. Watwood, H. Alvarez Pol, D. Bazin, M. Camaño, J. Chen, M. Cortesi, B. Fernandez Dominguez, S. Giraud, P. Gay, S. Heinitz, R.J. Evidence of a near-threshold resonance in B11 relevant to the beta-delayed proton emission of B11. Physical Review Letters, 2022, 129, 1, doi. 10. 1103, Phys. Revlet. 129. 012501 Michigan State University. Thanks for watching. Please subscribe my channel for more videos.